Mayor Timby is running for president and wants to know how many people would vote for him. He needs more than 50% of the votes to win. You don't have the resources to ask everyone. Nor do you want to. You have hobbies. So you randomly ask 100 people and call it a day. Afterwards, you tell him that 56% of the people you asked would vote for him. It's all good to know the proportion in your sample. What he would really like to know is the proportion in the population, specifically whether it's more than 50%. If he's smart, he would also ask, how sure are you? Is it between, say, 40 and 60%, or 20 and 80%? It makes a bit of a difference. So first, he wants to use the response in the sample to estimate what would be the likely response in the population. Second, he wants to supplement the point estimate with an interval estimate. A point estimate is when you're estimating using one number. An interval estimate is estimating using a range of values. These are just the jobs for the hypothesis test and confidence interval. The sampling distribution of the sample proportion is approximately normal. It's centered at the population proportion p. The standard error is the square root of the sample proportion, p hat, times 1 minus p hat, all divided by the sample size n. Under the sampling distribution, there's a 95% chance that you get a sample proportion within 1.96 standard errors of the population proportion. How did we get 1.96? We want to find the quantiles that would give a probability of 0.95 in the middle of the standard normal distribution. This leaves 0.05 across the two tails. In the previous section, we found the critical values that would give a probability of 0.05 across the two tails are minus 1.96 and 1.96. So there's a 95% chance that the sample proportion p hat is between the lower cutoff of p minus 1.96 times the standard error and the upper cutoff of p plus 1.96 times the standard error. We use the approximately equal to sign because we're using the normal distribution as an approximation. This gives you an interval around the population proportion within which the sample proportion is likely to be. We can rearrange the probability to find conversely the interval around the sample proportion within which the population proportion is likely to be. First, we minus the population proportion p from each term. Second, we minus the sample proportion p hat from each term. Third, we times each term by minus 1. Under math rules, this flips the inequalities. Then we rewrite the whole line so that the inequalities are in the other way. This tells us there's a 95% probability that the population proportion is within 1.96 standard errors of the sample proportion. The shorthand to write the 95% confidence interval is p hat plus or minus 1.96 times the standard error. Now you have a random interval that has a 95% probability of containing the population proportion. When estimating the population proportion, if you use just one number, the sample proportion, it's unlikely to be exactly at the population proportion. However, from that one number, you can get a range of values that has a high probability of containing the population proportion, which makes your estimate much more reliable. Because confidence intervals are random intervals, if you get a different sample, you get a different confidence interval. The way to interpret confidence intervals is, if you keep drawing a random sample and constructing a confidence interval using each sample proportion, you'd expect 95% of the confidence intervals to contain the population proportion. What you have is one of an infinite number of possible confidence intervals. In general, the confidence interval for any probability 1 minus alpha within the quantiles minus z star and z star has this form. Where p is the population proportion, p hat is the sample proportion, plus minus z star are the z-scores that give a probability of 1 minus alpha in the middle of the standard normal distribution, and n is the sample size. This is called the 1 minus alpha confidence interval. For example, We just went through a 95% confidence interval. The alpha is the significance level, such as 5%. 1 minus alpha is called the level of confidence. Plus and minus z star are the critical values. The length of the interval on either side of p hat is the margin of error. You put your best guess for the population proportion, which is the sample proportion, at the center, and then add a margin of error in both directions. You'll see that the confidence interval for any parameter follows this structure. The formula shows there are two reasons why you can get a wide confidence interval. The sampling distribution is really spread out, so you need larger critical values to cover the same percentage in the middle, or you have a small sample. Both make it harder to estimate what's in the population. The higher your level of confidence, the wider the confidence interval, so the more likely you are to capture the parameter. There's a trade-off between confidence and precision. If your confidence interval is -infinity to infinity, then you can be 100% sure that it would capture the parameter, but it wouldn't be very precise. If your sampling distribution is not very spread out, then your confidence interval will be narrow, and it may be less likely to contain the parameter. The only thing that the sampling distribution, and thus the margin of error, takes into account is the sampling variation, that if you pick a different sample, you may get a different value. It doesn't take into account every single thing under the sun. So if your sample is biased, or you don't record the answers correctly, or people lie when they respond to your survey, these would lower your confidence level and make the confidence interval wider, but the formula would not capture this. If you have other sources of errors, they wouldn't be reflected in the confidence interval. That's why in practice you have to be very careful. See our Statistics in Excel course on how to calculate the confidence interval for a proportion using Excel. We've done a hypothesis test for HO being p equals 0.5. You could have done a hypothesis test for p equals 0.51, p equals 0.52, or any of a million other numbers. Each time you would have gotten an answer. Yes, you can reject HO, or no, you can't reject HO. Rather than testing one value at a time, is there a way to find the range of values for which you'd reject or not reject HO? Yes, there is. You can use confidence intervals. Confidence intervals are like hypothesis tests in reverse. With hypothesis tests, for any HO, you identify the sampling distribution, and then you reject HO if your test statistic is too far from the hypothesized value at the center of the sampling distribution. For any significance level, there's an upper cutoff and a lower cutoff that tells you just how far is too far. With confidence intervals, what you're trying to find is how high or how low the parameter can be for HO to not be rejected. So you position the test statistic at the lower cutoff of the sampling distribution to see how high the center of the sampling distribution can go, and position the test statistic at the upper cutoff of the sampling distribution to see how low the center of the sampling distribution can go. This gives you a range of possible values of the parameter for which HO would not be rejected if you got that test statistic. This way, you can use confidence intervals as a shortcut to a two-tailed test. To instantly do a hypothesis test of P equal PO, just see whether PO is inside the confidence interval. If it is, then you can't reject HO. If it's not, then you can reject HO. The 95% confidence interval for the proportion of people who would vote for Mayor Timby is 0.46 to 0.66. The sample proportion is 0.56. In the previous section, we found that the critical values for a 95% confidence interval are -1.96 and 1.96. The sample size is 100. The hypothesized proportion of 0.5 is inside the confidence interval. Therefore, we can't reject HO. This is consistent with the two-tailed test. But can you see how much quicker it is? For more lessons on statistics, visit alphas&betas.org.